We're ready to start our next chapter, which is going to be a study on integrals and solving differential equations. Now, a lot of times kids look at that and say, wait a minute, didn't we just do that? Well, in fact, we actually did. And for one, you're going to find out that we continue to look at integrals. And for two, you're going to find out that that's actually the same thing as solving a differential equation. And for three, all of those are antiderivatives. And we end up having some different words that essentially all mean the same thing, and that is to try to do the first half of the year backwards, again, known as a antiderivative. Now, why are we going to keep studying this? Well, you'll discover that the problems that we do are going to progressively get a little harder because we're going to move beyond the basic integrals, the basic reversing of the first half of the year, and we're going to get into more complicated reversing, which we'll get to. Really, in this first section, we take one more a day, and we kind of focus on the rules. And when you reverse a rule, you're just trying to think of what we did the first half of the year, is just trying to think of how to do that rule backwards. And of course, a lot of those rules we've been doing, but one more time, one more day, we're going to focus and explore a couple new things about the rules. Before I give you the little activity where you guys are going to organize all the rules, let me just make sure we understand when we say integral. And so consider with me the integral of 1 over x plus 2 minus 1 over x squared dx. And I'd like you to consider that integral with me because, well, there is something new about it. Yes, it's missing the limits of integration. It doesn't have the a to b. Now, what that means is the answer to this problem is going to be the antiderivative for the sake of being the antiderivative. We're not going to actually subtract f of b minus f of a. The other reason I'm doing this problem is because there's never a bad time to think about fractions. They tend to bug kids. And so here we are looking at a fraction once again and trying to figure out the antiderivative of 1 over x plus 2. Now, anytime you see 1 over x or 1 over x plus a number, it's always going to be ln. It's always going to be ln because basically that's the reverse of that rule. However, when you see 1 over some other x, in other words, to some other power, well, it's first of all never going to be ln, and instead it's always going to be a negative exponent. Now remember, if you add to a negative exponent, in this case, if I add to negative 2, I'll then have to divide by that new exponent, so I'll have to divide by negative 1. Further, I've got this subtraction sign to kind of work into this overall answer. And I'd like you guys to quickly be able to recognize how this all shakes out. So we've got a minus sign and a negative. Well, they're going to cancel. That's just going to be plus. We also have x to a negative 1, which the sooner you can write that as 1 over x, the better. Okay, so 1 over x is an ln. 1 over x squared, it's a negative exponent, and then you work it out. Now, remember how we discovered that there could be a plus c at the end of any of these antiderivatives? Well, we're back to that because, well, simply it's not going to subtract away. It's not going to subtract away because we're not subtracting. So plus c will now be tacked on to our answer. What does this solve a differential equation? Maybe you're just wondering, what is a differential equation? Well, first of all, a differential equation is just a derivative. It's literally a derivative equation. So if I give you dy dx equals negative secant squared 4x, so I'm giving you the derivative equaling negative secant squared times, or of 4x, excuse me. To solve that differential equation really means to go back and find the original equation. To really do the antiderivative. Okay, now maybe you're just thinking, well, how do I do, what's the antiderivative of secant squared? That's fine, but I just want you to notice one more time, this is a derivative, this is the original equation. Once we find it, we will have solved the differential equation. Solving means go back and finding the original. Okay, the derivative of what is secant squared? Remember, you stood at my desk and you said the derivative of tangent is secant squared. So it's going to be tangent of 4x. We've got some other stuff to take into account. First of all, there's a coefficient. Coefficients always come along for the ride. So you can't go wrong by keeping the negative sign. Second of all, you got to notice at least that there's something else inside here with x. Now, when that was a derivative, we would have did the chain rule. We would have multiplied by 4. But since that is now since it's an antiderivative, we're going to do the opposite of multiplying. That's right, we're going to divide by 4. And you guys are going to see that on the little activity you do where you organize the rules. You're going to see dividing by k. Dividing by k. It's a little bit nicer, honestly, to write that as 1/4. I'm not going to take off. It's not a big deal, but it is a little nicer to write this as negative 1/4 tangent of 4x plus c. Now that is the solution. Notice the solution is an equation. And really, it's the antiderivative, which is going to end up being the solution to just about all the problems that we do in this chapter. Okay, now what I want you to do is organize those derivative, antiderivative rules, and then let me check them, and you can then copy them down one last time to have as a reference for the rest of this chapter. What we're going to do is kind of one more time, in somewhat of a basic way, we're going to evaluate some integrals. We're also going to solve some differential equations. If you're still kind of wondering, well, what does that mean? It all means the same thing. And it means we're going to find the antiderivative. Now, the problems that we're going to be doing, they now become a little harder because they just got a few more numbers. As I spoke with everyone individually, learning how to do the k thing, which is to divide by k, and really just kind of recognize how we can just keep using these rules. Okay, but just so you know, this isn't what we're going to be doing like next month. What we're then going to do is we're going to be looking at how to reverse some of the processes from the first half of the year. Right now, we're just reversing a few more rules. So if you're asked to do the integral of e to the x over 4 minus e to the 3x, I'm sure you can already tell that it's more than just e to the x. Okay, we've got a little more going on here. Good news, it's still the antiderivative. Remember, there's no limits of integration, so that just means that we're not going to do any subtraction. And if it's okay, I'm actually just going to put an equal sign here. I don't need to use capital F of x. You can say capital F of x, but I can just go right to the answer. Now, according to the rule on the paper that you guys filled out, the derivative of e to the x is e to the x. You can't go wrong by writing that down. But if there's more to the e to the x, then it all comes with it. It's going to be e to the, now I'm going to write this as 1/4 x, because I want you guys to see that k, listen carefully to this, k equals 1/4. Okay, it's always the number that's multiplied to x. So we're going to divide by 1/4. Well, are we really? I mean, you can write that, but are we really going to divide by 1/4? That's the same as multiplying by 4. So again, I divided by k, but let's make quick work of that. Let's write it the right way. Okay, e to the 3x. Well, again, it's an e to the x, so it's the same thing, but that means I got to bring the 3 with it, so the antiderivative is e to the 3x divided by k. K is always a number that's multiplied to x. Pretty easy to say we're going to divide by 3. Now you can write divided by 3. It kind of fits a little bit better with the style of the answer to say 1/3, but that's the same as dividing by 3. Plus C. Plus C. The reason we're back to the plus C is we figured out the first time we did this, there could be any number at the end of that equation that would make it equal to what I started with. I'm trying to show you as many, so to speak, new things in just a few problems. So every one of these is purposely a little bit harder. So we'll welcome this cube root of x squared. It's the cube root of x squared, and it's also being multiplied by -4. Now, -4 is not the letter K. Okay, you already saw this in the last chapter. -4 is a coefficient. So good news, coefficients always come along for the ride. You never change them. They don't divide, they don't cancel, or somehow disappear. So, boom. How about this this goofy cube root of x squared? Honestly, it's probably more algebra than it is calculus. You remember that the cube root of x squared is the same as x to the 2/3. Now remember, the numerator is the power, the denominator is the root. So we either write it as x to the 2/3 or we just think it, so that now we can, well, use the rule we've often used, the reverse power rule. You add and divide. Now there's probably a little more going on here that you want to make sure you're aware of. That is, we're adding some fractions, 5/3. We're going to divide by 5/3. I am going to actually write that because I want you to see that the new exponent is 5/3. But since I'm dividing by 5/3, that's the same as multiplying by the reciprocal, which of course is 3/5. 2/3 plus 1 is 5/3. But when I divide by 5/3, it's like multiplying by 3/5. And then definitely I would expect you to clean up house here and write this as 1 -12/5. You should write that as -12/5 x to 5/3. Plus C. Don't forget the plus C. I'll say nicely, if you do forget it, just once, we just kind of say forgiven. But if you don't write it on any answer, then unfortunately we have to lose some points. So just take an extra half a second and write plus C. Please don't interpret this that I already expect you to know what I'm doing. I'm purposely picking out some harder problems. These were integrals. How do you do an integral? It's the antiderivative. How about if you're asked to solve a differential equation? How do you solve a differential equation? You do the antiderivative. Now, it kind of is presented to you a little differently. It's presented to you as dy dx. But that actually makes it a little more clear that, hey, that's the derivative. That's the derivative of what? Well, that's what the solution is. The solution is the original y = equation. Again, otherwise known as the antiderivative. So it's the same thing. This problem is not hard. You have solved this before. I'll make sure that we don't overthink this. I expect that you're adding to the exponent. I expect that you're adding to the exponent and dividing. So again, it's pretty much the same thing. I just want to make sure that you realize that's what it means to solve an antiderivative. Excuse me, solve a differential equation, and that is to find the antiderivative. Let's do another differential equation. If somebody says that dy dx equals 3 over 1 plus x squared, if dy dx equals 3 over 1 plus x squared, It can look a little scary. It can look a little scary. And maybe you're fine. I can tell by some of you that you already have the right answer, but I just want to just show it that you're going to want to always interpret this as 1 over 1 plus x squared. Now, of course, that 3 doesn't just disappear, but that 3 is just a coefficient. Now, when you see 1 over 1 plus x squared, we do want to quickly say, oh, yes, inverse tangent. Okay, so it's a rule. That's what all these are. They're rules. Now, it's 3 inverse tangents plus c. I've got one more differential equation, and then we have what's known as an initial value problem, which none of what we're doing today is that earth-shattering, but it's kind of one more time to make sure you're good with the rules. These rules then will show up in every problem we do for the rest of the chapter. But again, we'll be doing processes. It'll be very interesting. Okay, a little more challenging, but good stuff. All right, I was just making sure I was seeing this correctly. This looks like a bucket of fun. The ln of 16 times 4 to the 2x. Maybe there's different things that are grabbing your attention here. Notice, well, let's let the x, let's let that be the big grab. X is in the exponent. It's exponential. If you look at your little sheet that you copied down, when something's exponential, the answer is the same. Okay, so 4 to the 2x is a big part of this answer because it's going to be the same. ln of 16, it's actually just a coefficient. Don't overthink it. Don't do something silly like 1 over x or something. ln of 16 is just a number. It's just a coefficient. Well, coefficients come along for the ride, so bring it along. Now, there is something in your little rules that you copied down that is very important for this problem. First of all, you always divide by the ln of the base. I'm talking about the 4 right here. You always divide by the ln of the base. And that's, you actually saw that in the last chapter in a couple problems. But look, there's a k. I want you guys to recognize k as any coefficient on x. And trust it, you always divide by k. Now, I'm already dividing, so I don't need to put extra division signs. So I'm going to also divide by 2. Be careful. I'm trying to keep those separated. It's not the ln of 8, okay, but it is the ln of 2. What do you guys think about the rules for that one? It is just a rule, but it's got the most parts to a rule. There's something that's going to happen here. And it's just kind of one of those things. There's something that's going to happen. I have to take you back a little bit to logarithms to help you understand something. ln 4, 2. ln 4 times 2. It's more common to see that written as 2 ln of 4. It's more common to see this as a coefficient. And depending on your knowledge of logarithms, which even if it's small, we can try to start learning that it is true that a coefficient is able to swing up as an exponent, or vice versa, it could swing down as a coefficient. So that 2 is able to become an exponent on 4. 4 squared, 16. Maybe you would have guessed, maybe you wouldn't have guessed, but the denominator is the same as the numerator. They're going to cancel. So the final answer ends up being 4 to the 2x plus c. Notice where I put the plus c. It's just at the end. It's not like in the exponent or something different like that. We don't say this much, but it doesn't hurt to remember the derivative of this cute little guy. The derivative of this is this. Okay, so basically if you follow the derivative rule, which will use the chain rule and will also use some logarithms, it will quickly go back to where we started. Okay, of course, that's always true. Initial value problem. Sometimes the bark's a little worse than the bite. Sometimes it kind of seems like, oh my gosh, what's this going to be? Well, once we get into it, you'll probably be like, oh, of course that's what it is. But I want you to hear the phrase, solve an initial value problem, okay? Because that's a common direction that's given. First off, you're still going to solve a differential equation, which means you're still going to do an antiderivative. Now think about this. When you solve a differential equation, when you find y equals, like we've done for all these problems, when you find y equals, it's like you're finding the original equation. The initial value piece is just going to ask you to get the exact c value. And if you look at all these problems up here, the c value is always at the end. And of course, the number at the end is always the y-intercept. In other words, the initial value. Okay, it's kind of fancy talk for find the y-intercept. Now, to do one of these, you have to be given some information. You have to be given some information. So I'll tell you what, let me go back over here. The information will have the directions. I'm going to write it out. You decide if you want to. And then you'll have a differential equation. So how about we do something with a trig function since we didn't do one of those today. And there'll be something at the end that you can't ignore. And that will be kind of like the little tip off that this is an initial value problem. Because basically at the end of this problem, it says that y of pi over 2 equals negative 2 is like giving you a point on the line. It's giving you a point on the line. And I could bet the bank you're going to do the right thing with that point. So let's see. Let's see if I'm right. Listen, I put this problem up here so we could one more time say that's a coefficient. Okay? Coefficients always come along for the ride. It's not a k value. The truth is there is no k value for this problem other than 1, so we don't need to bother with that. But you are going to do the antiderivative cosine, as you guys correctly matched today. But you've been doing a nice job with that. That's certainly sine. Plus c, of course, gives us the opportunity to find c. Okay, so do you see where these two numbers go? They go right where they want to go. They go into the equation for, obviously, for y and for x, or pi. Check that for theta. And just like you did in an Algebra 1 class, again, it's really like you're just solving for the y-intercept. Sine of pi over 2. Okay, sine of pi over 2. Maybe you don't want to get your calculator out. I don't really care if you do, but I know that some of you are going to be in a class where you can't, like in college. Pi over 2 is right here. It's actually right here. It's a rotation. Pi over 2 is 90 degrees. This point right here is the sine and cosine. It's actually the cosine and sine. So I end up with the number 1. Sine of pi over 2 equals 1. So we got ourselves a pretty easy little guy here to equal negative 4. Now, your final answer might seem a little redundant, but it's the full equation. Make sure you understand that the answers to the problems we're solving in this chapter are actually equations. They're probably not going to be numbers anymore because we're not actually finding the area anymore. Instead, we're finding the antiderivative for the sake of finding it so that you can apply it to some other things, which I'll show you. But right now, we're just finding the antiderivative. So we want to write out the equation. Now, we don't do this much, but I have basically a mini assignment, okay? It's not busy work. It's not just if you want to do it. It's an easy grade. Well, it should be an easy grade, but it's made up of all these types of antiderivatives. Okay, and if you're so motivated, you probably can knock out over half of these right now. Don't hurry up and rush, but if you want to knock out some of these, this would be something to do next class period. Okay, just kind of like a simple little nightly homework, but it is something that's going to be due and we'll ask you to turn in.